Okay, I zoomed the camera a little bit more than typical, just in an attempt to hope that you can see the board if I start writing on it. But let's pick up where we left off last time. We were talking about a group of people. We could define a group of people really simply, very iteratively, by saying, well, two people's a group of people, or three people, or four people, or five people, and so on. We can go on forever, like to infinity. Or we can define this thing recursively. We can say a group of people is two people, or a group of people is a group of people plus one more person. So, given that I know two people is a group of people, I would therefore know that three people is a group of people, because two people is a group of people, plus one more person would be three people, and by the definition, that gives us a group of people. And then, because I know three people is a group of people, I then also know that, well, 3 plus 1 is 4, and if three people is a group of people, 3 plus one more person must therefore also be a group of people by the definition. So that's very constructive, but we could also work our way down. We could say, I wonder if 5 is a group of people. Well, I don't know. But if I take 1 away, I would then have 4 plus one more person. And if I knew if 4 was a group of people, I could then tell you if 5 is a group of people. But I don't know if 4 is a group of people. So I'll take one person out. So now it's 3 people, plus one more person is a group of people, plus one more person would be a group of people, if 3 was a group of people. But I don't know. So I have to remove one more, then I'm left with 2 people. If 2 people is a group of people, then I know 3 people is a group of people, because that'd be 2 plus 1. And I do know, by the definition, that 2 people is a group of people. So because 2 people is a group of people, then I know 3 is a group of people, 4 is a group of people, and 5 is a group of people, and so on. So it's pretty handy. Usually in recursion, we're going to want what we call a base case, and then a not base case, like the recursive step. For those of you that are more familiar with math, you might find a lot of similarity between recursion and induction, which is interesting, but we won't go into that really in this class, but it's interesting to know. So the base case is a very clear definition, and the recursive case, not the base case, defines itself in terms of itself, which is weird, but I mean, it actually makes sense in our situation. It's weird when a lot of time when we're playing around with the definitions of recursion, we like to say, like we like to not include the base case, and we like to, oh, the recursive case defines itself in terms of itself, isn't that funny? I mean, it sounds kind of weird, but once we, take our time to explain it, it's not that bad. It's kind of fun. And recursion pops up a lot in math, which kind of means it pops up a lot in nature, but again, that's a little outside the scope of right here. So, a sequence of characters. A definition, we could do an iterative definition of a sequence of characters. Well, that could be 1 character, 2 characters, is 1 character, is that a sequence? I guess it's up for us to define. Maybe it is. And then 2 people is a sequence, and then 3 people is a sequence, and then people. Why am I saying people? Characters. Another character would then be a sequence, and so on and so on and so on, all the way to infinity. But we could also define it recursively. We could say like, well, 1 character is a sequence, and then a sequence plus another character would also be a sequence. So that could be our recursive definition. Although I'm assuming I want my base case to start at 1 character, maybe I would want it to start at 2 characters before it's a sequence. Or maybe I could even include it as no characters. I suppose I could define it that way. Perhaps like an empty set of characters, like an empty sequence, is also a sequence? I don't know. That's up for us to define, I guess. Point is, we can define it this way. A series of numbers. Well, 24, 88, 40, 37. Let's define a series of numbers recursively. A series of numbers is a single number or a number followed by a comma followed by a series of numbers. Might seem somewhat contrived, but let's think about it. I mean, we can do it constructively or deconstructively, but in this case, we've got a question. Is 24, 88, 40, and 37 a sequence of numbers? Well, let's apply the definition. Okay, a series of numbers is a single number or a number followed by a comma followed by a series of numbers. All right, well, I clearly don't have a single number here, so I'm going to have to do a little bit more digging. So 24 is a number, and it's followed by a comma. Therefore, it's a series of numbers if and only if 88, 40, and 37 is a series of numbers. I only know if I've got a series of numbers if the remaining bits are a series of numbers. This is like the recursive step. That leaves us with 88, 40, 37. So is this a sequence of numbers? Well, 88 is a number, and it's followed by a comma. Therefore, it's a series of numbers only if 40 and 37 is also a series of numbers. So we have to ask the question again on 40 and 37. 40 is a number, followed by a comma. Therefore, it's a series of numbers only if the remaining bit, which is 37, is also a series of numbers. So let's apply the rule again. There's only the two rules we're applying here, the single number or the other one, the recursive one. So it's not complex. A lot of people get really worked up when learning recursion. They think it's complicated. But we're applying these simple rules. There's no new magic here. We're following all the rules we're used to since we started learning computer science. 37. Let's apply the definition. I know it's getting small. 37 is a series of numbers by definition. Why? Well, the first bit. It's a single number is a series of numbers. That's how it was defined. So if 37 is a series of numbers, that therefore means 40 and 37 is a series of numbers, which therefore means 88, 40, and 37 is a series of numbers, which therefore means 24, 88, 40, and 37 is a series of numbers. There, we're done. We answered the question. It might seem like a lot of work, but it's kind of fun. I just started saying this, but I want to take a note to emphasize this. A lot of people say, oh, recursion's hard to wrap your head around. And I suppose it's not that it's trivial to kind of switch into thinking from iteratively to recursively. It's not that that's trivial, but I always fear that people, by telling new computer scientists, people who are learning this stuff, by saying like, oh, it's hard, I fear that it sets people off on the wrong foot. It's not that bad. It does require a little bit of, switching your head a little bit, but it's not as bad as you might think. And I don't want people in here, or not here, watching on YouTube. I don't want people getting in their head like, oh, I was told recursion was hard. No. Just we're following the rules we've done before. It's definitely different than iterative, but I don't think that it's scary or terrifying. It's funny too, because there was a year during my undergraduate I took programming courses where I was using a programming language called Haskell. And in Haskell, it's a fun programming language, but it's a different style of programming compared to what you're used to in like your C, C++, Python, C#, Java, whatever. It's a little different. It's what we call a functional programming language. And with this particular language, Haskell, there were no such thing as loops. You weren't allowed to use like for loops. If you ever wanted anything to loop, it had to be done recursively. So there was no such thing as like a for loop or a while loop. It was all recursive. So anytime I wanted a piece of code to run over and over again, it had to be recursive. And I spent like a whole year only using this style of programming languages. That wasn't on purpose, it just kind of happened that way by the courses I picked. Then, when I went back to, I think it was Java, I actually had a hard time wrapping my head around iteration. I had a hard time remembering how to use loops. And it's just based on what you're used to. It's not that one is necessarily easier than the other, it's a different way to solve the same problem, which is kind of fun. So, the only reason I told you that story was because it just puts in perspective that, no, it's not harder. It's not this weird new concept. It's actually just the same concepts. We're just using it to do loops, and you can do one or the other. It's different, and it takes a little bit for your brain to kind of like switch to getting it if you're only used to the one, but you'll get it. So, is it a series of numbers? Yeah, we just went through this. Blah, 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 blah. Okay. Now, we can actually even define a data structure recursively, like a list. Now, we were defining lists before, but for fun, let's define lists recursively, with a recursive hat on. So, A, B, C, D, and E, is that a list? So, we could consider the fact that all lists can be broken down into its head, followed by the rest of the list. Basically what I mean is, we have A, B, C, D, E. I will say the head of that list is just the thing at the beginning, A. And then the tail is everything else. It's B, C, D, E, let's say. Okay, so that's our definition. We can take the head followed by the remainder of the list. So, just like that. We have A, B, C, D, E. Okay? That's something we need to keep in mind. Head, remaining bit. We can call the remaining bit the tail, but it could be arbitrarily long as well. It's not like a single thing. It's not like the end of our, it's not like the end of the queue or the list or something as before. It's the whole rest of the bit. So we can define our recursive list as an empty list. Okay? A list that has nothing in it is a list. Why? Because we said so. That's how we're defining it. So an empty list is a list. A head that's an element followed by a tail that is a list. All I mean is, if I have a case where I have, just very, very simply, and we're going to see a bigger example of this in one moment, but very, very simply, if I have a head that, I don't know, A, it's the character A, followed by the tail that's an empty list, that's a list. Now imagine we didn't have this for a second, we just had this. That's just an empty list. That's how I'm going to write empty list. That is a list by definition, and this is also a list. I'm just going to erase this for a moment because I'm feeling we're going to go into a much bigger example as we go through the slides. So we've got our A, B, C, D, and E. Well, is A, B, C, D, and E a list? That's our question. So, is that an empty list? No. But it's a head followed by a tail. So we can take the A out, the head out, and then we have the tail, which is the rest of the list. B, C, D, and E. Then we can take the B out. Like, kind of pretend that A is not even there. Pretend we threw that away for a second. Obviously we didn't, but you can pretend it's not there. We just have the list B, C, D, and E. I can take the B out because it's the head, and then we're left with the tail, which is C, D, and E. Is that a list? Well, let's keep going, because we don't have an answer yet. So we've got C, D, and E. We take out the head, so we've got C, followed by the tail, which is the list D and E. Is that a list? Don't know. We haven't answered it yet, so we got to keep going. So now we have D. We take the D out of that list, and we've got the head D, followed by the list E. Is that a list? Don't know yet. Got to keep going. So let's take, here's a weird one. Let's take the head out of that list E. Well, what is it? It's just E. But what's the tail? What's left? Nothing. It's an empty list is nothing. This is kind of the trick here, is understanding that the tail of a list with only one thing is just an empty list. So now, do I have a list? Can I answer this question? We can. Because here, we know that this is a list, which means that this is therefore a list, because we have the head back in, which therefore tells us that that's a list, that's a list, that's a list, that's a list. Now we answered the question, is it a list? If you're getting thrown off by the fact that I've included everything here, you can think of it as repeatedly asking the questions like this. We have A, B, C, D, E. Well, let's take the head out. Okay, we have A followed by B, C, D, and E. Okay, now is this part of the list? Well, let's ignore this and let's just jump up over here. Take the B out of that list, knowing that the A is still there. So I'm only focusing on this part now. B plus C, D, and E. And then I would carry on. So in this example up here on the slides, I included all the previous heads as I went down, but we can kind of think of only focusing on the sublists as we go. And it might not be a bad idea to consider the fact that a list is kind of like a bunch of sublists grouped together. You might find it kind of silly to think of it that way, but you might also find it handy, especially going forward through your computer science degree. So just keep that in mind. It's kind of cool. Anyways, pardon me for one moment while I erase. Too bad there are people in here to ask questions. So the recursive definition will consist of two parts. A recursive definition consists of two parts. We already talked about them. You might already have the idea in your head. We need that base case, and we need the not base case, the recursive step. So our base case, it kind of defines like, here I've got like a starting point. It says starting point, but that's not necessarily the case, because sometimes it's not a starting point. Sometimes it's like the starting point. If we're going constructively, where it's like, well, two people plus one more person is a group of people, plus one more person is a group of people. That's kind of thinking of a starting point. But we could also consider it as kind of like the bottom. If we're kind of deconstructing, where if it's like, is 10 people a group of people? Well, that's 9 plus 1. Is 9 a group of people? Because then it's not really the starting point. We kind of have to work our way down to the bottom before we can head back up to answer all the questions. So it's not just the starting point. Keep that in mind. And we also have the recursive part. It's like the general case that describes all other cases in terms of smaller versions of itself. If you remember from last class, I did that example of asking people how many people, or how many rows there are in this room. And I asked the person at the back of the room, how many rows? But they don't know. They only know that the number of rows in the room is the number of rows that there are in front of them, not including their row, plus one more, their row. So it's kind of funny to think how lazy you can be. It's weird to think, but I like to think of recursion of being lazy. If I ask the person at the back, how many rows are there? And your answer is going to be, if you're sitting at the back, your answer is going to be like, oh, well, it's the number of rows in front of me plus 1. And you might think, well, hold on, you never asked how, like, you don't know the answer. But it's not your problem to find out the answer. You're going to call a function that's going to answer that for you. They're going to get back to you with the answer to that question, that it's the answer to that question plus 1. It's, how many rows are in front of me? I don't know. But I'm going to ask the person in front of me and they'll tell me. It's not my problem. Someone else is figuring it out. It's funny to think of it being lazy. We'll see other cases of this as we go. I'm going to talk about some interesting sorting algorithms that we did kind of talk about in 161. We talked about merge sort and quick sort very, very briefly. We're going to talk about them a little bit more. But with those sorting algorithms, well, we'll see, but you'll see how lazy the definition can be recursively. But it actually works. It's interesting. But more of that later. So a recursive function, of course, can have multiple base cases and or recursive parts. You're not limited to just like the two, but you have to have one of each. That's not necessarily the case. It is possible to not explicitly write like a base case, but it gets a lot riskier, that's for sure. Why have a base case? Well, I showed you last time. This example, we've got our function which just prints out wee, and then we call and we saw in this case we just kept pushing frames onto the system stack, and eventually we were going to get that infamous exception, the stack overflow. So we will easily have infinite recursion because this is recursive steps, but there's no like bottom of the bucket like I was talking about before, where we worked our way down to some base case and then we were able to go back up. In this, we're just going to keep working our way down to infinity and never come back. Which is kind of funny to think about computationally, but we're lucky because our computers, they're finite and they're going to stop. Here's a little joke someone found on the internet. It was in someone's textbook. I don't remember which textbook it is, but I do like it. Infinite loop, go to page 252. You go to page 252, look up infinite loop, go to page 252. See, it's kind of like an infinite loop because it's like a recursive call to the same page, no base case, haha. Anyways, going up and down, sometimes we start at the base case, two people as a group, our group, whatever. Or sometimes we end at the base case, our 4 people a group, and we work our way down. It's not really, I guess it's not really even ending at the base case. we get to the base case and then work our way back up. But sometimes the base case is the starting point, sometimes it's not, depending on how we use it. So, factorial. We talked about this last time. And defining factorial recursively is so much easier than any other way to do it. So, factorial and exclamation point. That means factorial, the exclamation point. So, the factorial of any positive integer is defined to be the product of all integers between 1 and n inclusively. We don't want to include 0 because if you multiply everything by 0, well, you lost it all. So it's only defined for positive integers, I guess. So here's how we can define it. 1 factorial is 1, or n factorial is n times n minus 1 factorial. So, if we have 3 factorial, well that's equal to, simply, look at the definition. Is that a 1 factorial? No. So we need to do n, which in this case is 3, times n minus 1. Well, 3 minus 1 is 2. 2 factorial. What's 2 factorial? I don't know. Is it 1? No. So we got to go to the other. Okay. So 2 factorial equals n, 2, times 2 minus 1, that's 1 factorial. What's 1 factorial? Well, that equals 1. Why? Because it says right there, by definition. So now I know if 1 factorial is 1, that lets me go here and replace 1 factorial with just 1. And then 2 factorial is therefore 2 times 1, which is just 2. So, because I know all that, I can very easily just do that. Don't need this anymore. See, we worked down, and now we're working our way back up. 3 times 2, well that's 6. Therefore, I now know 3 factorial is 6. It's pretty cool. Now, one thing kind of interesting to note too is, I now know that 3 factorial is 6. So if I wanted to know 4 factorial, I could just do 4 times 3 factorial, and 3 factorial is 6. The point I'm making is the answer to, the point I'm making is, if I wanted to know n factorial, what the answer to n factorial is, in the process of finding the solution to n factorial, I will also answer what the factorial is for all numbers less than n as well, that are positive integers. What I mean is, if I want to know 4 factorial, I have to know 3 factorial. So I'm going to have to answer the question 3 factorial. What's the answer to that? And in order to know that, I got to know 2 factorial as well. It's kind of neat. It's kind of like this is doing some extra bookkeeping for us. I wonder if it would be useful, or, I'm trying to think for a second, how would I go about defining this iteratively? Would it be useful if you asked me what's 5 factorial? No, let me say you asked me what's n factorial. How much work would that be to answer recursively, I'm wondering? Well, I'm going to have to answer n factorial, n minus 1 factorial, n minus 2 factorial, n minus 3 factorial, 2 factorial, 1 factorial. How many questions is that? Well, that's going to be n. It's going to be like order n to compute, right? So, it's going to be order n to compute. But, what if immediately after you asked me what n plus 1 factorial was? I would then have to calculate, well, n plus 1 factorial. I'd need to know n factorial. I would then need to know n minus 2 factorial, n minus 3, all the way down to the end. I would have to do all that work again. I'm repeating work, which is problematic. So, that seems kind of like a waste, right? I'm going to be repeating all that work. I just calculated n factorial. Now when you ask n plus 1 factorial, I have to calculate n factorial again. Seems kind of silly. would it be good to kind of do some bookkeeping, I wonder, so I don't have to repeat that work? You know, because repeating work seems like it might be wasteful. If I remembered what n factorial was and I just remembered it somewhere, like I wrote it down, if I go, oh, n factorial equals, I don't know, something, some value, x, okay? Then, if I wanted to know n plus 1 factorial, it's just n plus 1 times x. How much work is that to figure out? Assuming I already did all the work to calculate n factorial, I already have that number, it's saved. All I have to do is x times n plus 1. And now we've suddenly got an order 1 operation, which is kind of handy. I wonder if that's useful, I don't know. You'll figure that out later. Okay, so just did this, yeah. All the way back up. Bingo, there we did 4 factorial, cool. Of course, all these slides are online, so if I move too quickly, go get the slides, go through them slowly, take your time, you'll get it figured out. So iteration is repetition with loops. Recursion is defining something in terms of a smaller or simpler version of itself. And then we can do iteration that way, which is pretty cool. Well, like looping, at least. Recursion is an alternative to iteration. Anything you do with iteration, you can do with recursion. Although, just because you should doesn't mean you should. Or just because you could doesn't mean you should. Anything you can do with recursion, you can do with iteration. They're not, like, exclusive, but there are some things that are easier to do recursively than iteratively, and vice versa. And it should be noted, although this is strictly a consequence of how our computing machines work, how your laptop, how your desktop, how those things were built, doing something recursively can be a little slower. Because the computer needs to create those like call frames, push it on the stack, it's got to remember that memory, it's got to get all these pointers to jump around RAM. Recursion can be slow, but that is strictly because of how your computers are designed. Someone could design a computational system where recursion is not slower. In fact, when doing the math on the board, it's not that it's intrinsically slower because we're not like computing it with the call frames and whatnot. We're just doing it. So it's not like intrinsically slower. It is by a consequence of the engineering that went into your computers, your computing machines that you're using. Yeah, okay, just because you could doesn't mean you should. So recursive programming. Recursion can be used in programming where a function calls itself to solve problems, obviously. I mean, if I wrote that recursive definition mathematically of n factorial, but I could easily write it like a function, right? Like I could easily write like a C++ function to do factorial. So if we write a function that involves calling itself, we want it to be recursive, we need a base case and we need the recursive part. So consider the problem of computing the sum. This is going to be pretty darn similar to the factorial example. But now we want to know the sum of all numbers between 1 and n inclusively. If I were to go do this iteratively, this is really simple. Create a for loop, create some sum variable outside the for loop, set it to 0. Create a for loop for I starting at 1, going all the way to n inclusively. Just keep adding sum equals sum plus I. And at the end print out sum. We're good to go. Pretty sure that's right. So it's easy to do iteratively. Let's do it recursively. So this is what we want. Okay, it's easy to do iteratively. Oh, okay, there we go. I literally just said this. Haha, I was right. Perfect. There we go. I mean, I suppose I could have started I at 0 as well because adding 0 to 0 does nothing, but whatever. It's better this way. So there we go. This will give me the answer iteratively. It's nice. But we could think of this. So let's put our math hats on. The sum of all the numbers all the way to n, where k equals 1, is going to be this, or where k starts at 1 goes to n. It's going to be n plus the sum of all the numbers up to n plus 1. See how it looks really similar to the recursive definition of factorial? basically the same idea, but instead of multiplication, we have addition. But that's basically it. The sum of all the numbers up to n is the same thing as the sum of all the numbers from 1 to n minus 1 plus n. That's it. What's the base case? Well, that's just 1. So we could keep going. We could keep breaking this out. N plus n minus 1 will be the sum, pardon me, the sum of all the numbers from 1 to n minus 2 plus n minus 1 plus n will be the sum of all the numbers up to n, from 1 to n, inclusively. So if we write this recursively, here's how we do it. I guess I define my function, I called it rec sum for recursive sum, and we put in an n, and then we ask the base case, is n 1? If it is, then the sum of all the numbers from 1 to 1 is 1. Why? Because that's how it works. That's by definition. Otherwise, if it's not that, we want to find out what n plus the sum of all the other numbers from 1 to n minus 1, that's what the n minus 1 in that function is. See, rec sum n minus 1. That, when we answer that question, it's like, this is the same thing as asking the person at the back of the class, how many rows are there in the classroom? Well, I just need to know what the sum of all the numbers up to n minus 1 is, and then add n to it, and I'm done. That's it. I'm all set. Easy. How do we know how to do that? Well, great. I got news for you. We just wrote a function that does that. So put in the n you want. In our case, it's going to be n minus 1. So this is where the magic happens. Let me start over. I've got a function called rec sum. And I'm guaranteeing you, I know we're just writing it now, but imagine for a second that the function we're writing is guaranteed to be correct. Bear with me. I've got a function called rec sum. And it's guaranteed to give you the sum of all the numbers from 1 to some number. It's guaranteed to do that. Let's say I've got that. Okay. If I've got that, we're now on that last line, that return. If such a function exists, okay, bear with me. If such a function exists, where if I know I've got a function that's guaranteed to give me the sum of all the numbers from 1 to the number I want, inclusively, if I've got that, then it's trivial to ask what's the sum plus one more. Because then it's just going to be the sum of all the numbers up to the number before, n minus 1. I want the sum of all the numbers from 1 to n minus 1. And I've got a function that's guaranteed to do that. It's called insum. I'll call that function, it'll give me the answer, and then I'm just going to add n to it. I'm going to say that again, just to make sure we've got it. Pretend for a minute. Don't even look at this code. Perfect. If I told you, okay, let's get the base case out of the way. If I ask you the question, what's the sum of all the numbers from 1 to 1, your answer is 1. Why? Because it is. That's just what it is. So we've got that part of the way. Now the hard part is the recursive step. But the trick to doing this, the trick that you've got to do, like the switch you got to flick in your head to start thinking recursively is, let's pretend I've got a magic function, okay, called rec sum. Rec sum for recursive sum. I've got this magic function. Let's not worry what's in it, because we're writing it. Weird, but bear with me. I've got this magic function called rec sum that is guaranteed. Let's not worry about what's in it right now, but it's guaranteed that, so this rec sum is going to take a number, whatever number you want, and that function is guaranteed to give you the sum of all the numbers between 1 and the number you give it. This function, that's what it does. You're guaranteed to get it. Let's not worry what's in it. Just if you call it, it's guaranteed to work. If it exists, and you want to know the sum of all numbers up to and including n, well then all you have to do, because you don't know how to answer the question well, what's the sum of all the numbers up to including n, right? Because what you do know is you have a function though, and you do know that, okay, if I take n and add it to all the numbers up from 1 up to and including the number that came before me, and then I add n to that, I will therefore have the sum of all the numbers from 1 to n, right? Basically, take 1 less than me, the sum of all the numbers up to then, and then add me to it. I'm guaranteed to get the sum of all the numbers up to including n. Right? Take your time to chew on this. It's critical that you get it. This might also be where like induction kind of comes back in your head, if you remember induction from math, high school, or whatnot. But that's what this tells us. We've got our base case. If n is 1, it's 1. Then we're pretending that a function called recsum exists, that if you give it a number, it will give you the sum of all the numbers from 1 to the number you said. So I'm just going to call the function that does that, the special magic function, to n minus 1. Then we'll add n to it, and we've got the answer for the current n value. But then what if I wanted to know like the n plus 1th value? We'll just put in the n plus 1 in the original case. Then we'll do n plus 1 plus recsum of n, blah, 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 blah. I mean, if you plug in any number, if you don't believe me, grab your sheet of paper and a pencil and scratch out what the code will do. Keep track of all the variables as you go through. Keep track of all of that for some value like 6 or something. Don't go too big, you'll be doing it forever. But put in a value like 6 and then take your time, go through it. Time again. In fact, let's do that right now, just to have some fun. I'm going to say recsum rs. Rs of some value. I'm going to do 5 because I'm lazy. Okay? Let's go. So n is 5. All right, is n 1? No. Otherwise, return n. So that means 5 plus rs of n minus, well, that's 4. N minus 1, there. We create a new call frame and we're pushing it on the stack, but inside this call frame, n is not 5 anymore, it's n minus 1, which was 4. So, now we ask the question, okay, what's rs of 4? Well, that's easy, that's 4 plus rs of 3. Well, what's rs3? I don't know. This is a new call frame, n is now 3 inside this one. We've got call frames on top of call frames. In the bottom one, n was 5, and the one above it, we've got 4 as n, and the one above that, we've got 3. And now, rs of 3, well, that is 3 plus rs of 2. Might be running out of space on the camera, but rs of 2, well, that's 2 plus rs of 1. But I know rs of 1. And remember, each of these function calls creates a new call frame, which has a new copy of the variable n with a different value. The bottom one is 5, and then 4, and then 3, and then 2, and then 1. But we know the base case, n is 1. So, when n is 1, return 1. Okay, great. So this is now 1. 2 plus 1 is 3. So rs2 is 3. Three plus 3 is 6, so rs3 is 6. Six plus 4 is 10, so rs4, recsum 4, is 10. Five plus 10 is 15. rs5 is 15. Is that right? 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. Yeah, there we go. How about that? Huh. You know what's interesting? I could write this in a way where my base case, so here I wrote my base case, and I want to be clear, this is how I would write it. This is probably the easier way to do it. But I could have wrote this where my base case was if n is the stopping value, like if the value, the value being passed to the function is equal to the value I want to stop at, and then I start at 1 and then add. So I'll do 5. You know what? Let's not worry about it. Really, let's not worry about it. Ignore what I just said. So remember, any function method call is pushed onto the stack. Every time the function calls itself, we'll make a new call frame for that call and push it on the stack. Great. Okay, wait. I just said that. There we go. We're happy. Yeah, just did that. Cool. Great. Done. So, I think I already ranted about this. Notice how recsum 5 would have made a call to recsum 4. Meaning that recsum 4, the answer to recsum 4 is in the answer to recsum 5. But the answer to recsum 3 is in the answer to recsum 4, which is also in the answer to recsum 5. So that bookkeeping might be handy. We might be able to save a lot of time. Just need to know that. Okay, so yeah, if we call recsum 6, we're going to have to know the answer to recsum 5. We just answered that. So, just to know, there's relationships between the recursion and the stack ADT in general. Just because we can use recursion does not mean we should in practice. On the machine, okay, I already said this. Fibonacci numbers. Here is the Fibonacci sequence. There's a story about rats having pardon me. The story's about bunnies having babies. Bunnies get stranded on an island or something, and they start multiplying because they have a lot of babies, and this is how they multiply. The story goes something like that. But Fibonacci sequence is a very interesting, important sequence we like. What's the pattern? Take a moment, look at this. Pause the video, I guess, and see if you can figure out the pattern. I mean, really what it is, we start with 1 and 1, let's say. I've seen other definitions where we don't start with 1 and 1, but let's start with 1 and 1. The first number is 1, and the next number is 1. Now the question is, what comes after that? What comes after that? Fib 1 is 1, Fib 2 is 2. No. Fib 1 is 1, Fib 2 is 1. Fib 3 is 2, but why? Well, okay, I'll show you the recursive definition, and it should make good sense. There. Fib of 1 is 1, fib of 2 is 1, fib of n is the sum of fib of n minus 1 and n minus 2. Okay, what is fib 3? So fib 3 must be the sum of fib 2 plus fib 1, because 3 minus 2 is 1. Well, what's fib 2? Well, we know that, it's 1. Why? Because it says right there. And then why is fib 1 1? Well, because it says up there, by definition. So therefore, basically, the Fibonacci number is the sum of the two previous numbers. So basically, 1 plus 1 is 2. And then 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. 13 plus 21 is 34. 21 plus 34 is 55. 34 plus 55 is 89. And so on and so on and so on until the end of the universe. It just keeps going and going and going. That's it. Here's how I would define it recursively. This is a beautifully simple recursive definition. N is 1 or 2, return 1. Otherwise, return the sum of the previous 2. Look how simple this is. This is magical. Now take a moment and think, how would you write this iteratively? What would we want it to look like? How would I code this? Well, here's an example, one possible example of doing it iteratively. Take a second, look at the code. Okay, if it's 1 or 2, just return 1. Otherwise, prev cur is 1, and we define next. Start I at 3 and go all the way to n inclusively, I guess. Next is prev plus cur. Basically, we're just moving down. Right? It's calculating, we've got 1, 1, and I've got prev and cur. The next one is prev plus cur. So I make 2. And then I move prev and cur down. So cur should become next, and prev should become cur. So then we have these two. And then we move down. And we add these two. And then we move down. And so on. It's pretty cool. It's pretty handy. But of course, I mean, if you look at this code, and you look at that code, Which one do you like better? Which one is like beautiful? I mean, I look at this recursive definition and I think, wow, that's just, wow, like that's so beautiful. It's like the hair on the back of my neck stand up because it's just, wow, it's glorious. It's so simple. I love this. Look how simple it is. It's magical. But then I look at this and I'm thinking, oh, look at this. There's a loop starting at 3. Who likes loops starting at 3? And then, I don't know about you, but I like when my loops go from I to less than n, less than equal. Ugh. We've got all these variables and bookkeeping going on. It's so ugly. It's so gross. The recursive one. Look at this. Look. Oh, this is so pretty. And if you don't think so, you're crazy, because look at this. It's so nice. So, which looks easier to implement? Obviously the recursive one. It's like 4 or 5 lines of code. Now, here's the thing. So, we know that in practice, as I just said, that recursion is slow on our computing machines. By nature of how those were designed, they're slow. So, on one hand, we already know that, well, it's prettier, but it's going to be a little bit slower, I guess. Just by the fact that we already know that the algorithms are going to be slow on our computing machines. But remember, that's on our computing machines. That's the fault, not of the recursive definition. It's the fault of how the computing machines were designed, not by the mathematics behind those algorithms. It's important to distill the difference between those things. So, let's ignore that fact for a second and actually investigate the computational complexity of what's going on here. So, okay, we have to do the iterative analysis and the recursive analysis. Which one's faster? Which algorithm is better? So, if we assume that the computational complexity is what's important, the fact that the computing machines that we're using are a little slower for recursion because of the fact that we've got to create call frames, push them on the stack, pop them off the stack when we're done, that overhead. Let's ignore that. Let's pretend we're working on a computing machine somewhere that it doesn't matter. So have a look at this one. This is the iterative one. How much work is taking place here? Well, take your time, pause the video, see if you can figure it out. It's not too hard. It might look complex, but it's not too hard. If I want to know the Fibonacci number n, some arbitrarily large n, how much work's going to happen here? Well, we have to find out. If I want to know, based on how this is written, remember, pause the video, try to figure it out for yourself. But if I want to know the Fibonacci n, I need to know the answer to n minus 1, and then n minus 2, and then n minus 3, and n minus 4, to 2 to 1. How much is that? Well, that's n. It's linear. I have to go back and calculate all previous ones. So it's linear. That's not bad. I mean, that's reasonable, I guess. But, yeah, linear. Now let's think about this one. How much work is being done here? Well, so far in this class, we haven't seen how to do complexity analysis on recursive things, right? We've seen complexity analysis on like the iterative things with the loops and whatnot, but what's the complexity analysis here? Okay, let's think for a second. Hopefully the camera picks up what I'm about to draw, because this is going to be critical. But let's think. If I want to know the Fibonacci of n, what do I need to know the answer to? I need to know the answer to fib n minus 1 Note that each of these is a fib call. Each of these is a fib function call. So this is like fib of n. I need to know fib of n minus 1. But in addition to knowing fib of n minus 1, I need to know fib of, in addition to knowing fib of n minus 1, I also need to know fib of n minus 2 to add them together to tell me the answer of fib of n. So, in addition, I need to know fib of n minus 2. Great. Okay, so, what's fib of n minus 1? Okay, well, this isn't too bad. Let's just follow the same rules, except now n is n minus 1. So if n is n minus 1, it's going to be n minus 1 minus 1. So I need to know the answer to fib of n minus 2. And then fib of n minus 1 minus 2 is fib of n minus 3. So I need to know the answer to this in order to answer this. Fib of n minus 3. Right? And then of course over here, in order to know the answer of fib of n minus 2, I need fib of n minus 3 and fib of n minus 4. And then here I need to know, oh my goodness, I'm running in a row. Fib of n minus 4, and then here I need fib of n minus 5. But I gotta keep going. I mean, over here I need fib of n minus 4, fib of n minus 5, and then over here I need, you see the problem? And then of course over here, I'm not done over here. I've got fib of n minus 3, fib n minus 4, then over here I've got fib n minus 4, fib n minus 5, and then here I've got fib n minus 5, fib n minus 6. I mean, I'm running out of, but do you see how this is growing? First of all, look at this tree. Do we see a problem at this tree? I mean, I'm throwing you to the deep end here. This is fairly complex. But can you identify the problem? Now, let me take a second and make sure we understood. If we were to do it iteratively, not recursively, this is the rec one. A big R for rec. Big I for iterative. Hopefully you can see this on the camera. If I did this iteratively, if I needed to know fib of n, well, I need to know fib of n minus 1 and fib n minus 2 and fib of, but that's the linear. It's just linear. Because in order to fib n minus, here it's growing like a tree, which is kind of crazy. Notice how, okay, if I want to know fib of n, I need to know fib of 1 and fib of 2. Or pardon me, fib of n minus 1 and n minus 2. So you will notice that this tree will go on until we get to like fib of 1 or 2 is at the bottom. Finally we get to the base case at each of these trees. This one will only go down until it hits like 1 or 2. Actually, that's not even the case. This one's going backwards. The one before, it actually started at fib of 1. This is wrong. Really, I was doing fib of 1, fib 2. And then if I wanted to do any other one, I would just build up. Fib 3, the sum of these two, then the sum of these two would be fib, and so on. So this is wrong, so I started it and worked my way backwards. This is really what it is. Starting at 1 and constructing it. So here, imagine this tree goes down all the way. There's a lot of work going on in fib of n minus 2. It's this whole subtree that goes all the way down to the base case. There's a lot of work going on there, but I'll eventually answer it, right? But look, I've asked the exact same question here. And of course, this tree goes on until it hits the base case. I've answered the question in this tree. To find out the answer of fib of n, I've asked and answered the question, what's fib of n minus 2 and fib of n minus 2 twice. I did the same work twice. Now, let's think for a second. Can we figure out what the computational complexity of this is? Let's see if I've got it in the slides, because they might help visualize it a little bit. If not, we'll come back to the tree itself. So, there we go. Fib of 6. Well, we need to know fib of 5, fib of 4. But then in order to know fib of 5, you need to know fib of 4 and fib of 3. In order to know fib of 4, you need 3 and 2. And then here you need 2 and 1. Ah, well, there's base case. You can work back up. But then fib of 2, well, that's another base case. Work back up and so on. But you'll see, how many times did I answer the question? What's fib of 4? Well, I asked it once. Let's see if I can draw here. I asked it once here, and I asked it once here. But how many times did I ask what fib of 3 was? Well, I asked it once here, asked it once here, and asked it once here. I mean, you can see that I'm starting to ask the same questions and answering them over and over again. That's a lot of wasted computing power. Asking and answering the same questions again. That's a lot. So let's think of the computational complexity. You might be intimidated by this, but let's just put our math hats on for a second. Okay. Okay, we're going to be lazy. We're going to be lazy computer scientists. Let's not get worried about being too precise. What is the depth of this tree? We haven't talked about trees yet, but this is a tree. See how things kind of grow like an upside down tree. What is the depth? Well, it looks like the depth is going to be like order of n. So we got fib, in order to know fib 6, we need to know fib 5, 4, 3, 2, and 1. I guess the base case on the far left over there, you know, we really didn't need to go down anymore. But we're lazy, so it's on the order of n. Okay? So there's like n levels to that tree. Okay? So if we have n levels, how much work is being done at each level? If we knew how much work is being done at each level, that's not quite true, because it's not the amount of work being done at each level, it's more about like how much work is being done in total. Well, how much, I've got n levels. Okay, for each, how about this? How about for each level, how much more work is being done on the next level? So, okay, on the first level, there's only one thing. How many questions have we asked on the next level? 2. Then, how many questions are we asking in total for the next level? 4. It's like we're doubling every time. It's like we're doing 2, 4, 8, 16, 30. I mean, if we kept going, we're going to be in big trouble. Here we've got 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Remember, don't just think fib 6, think fib n, where n is some arbitrary large number. It's going to go 1, 2, 4, 8, 16, 32, 64. That's like 2 times 2 times 2 times 2 times 2 times. How many times? Okay, if it's 2 times 2 times 2 times 2 times 2, how many times are we multiplying it by 2? Well, how many levels are there? N. That's going to be like order 2 to the n. This one was order 1. Not 1. Order n. Linear. We like linear. Here, it's order 2 to the n. And for those of you that remember from our little discussion about computational complexity, how bad is 2 to the n? It's pretty horrible. So, at the end of the day, I was ranting about how beautiful this recursive definition is, but really, it's horrible computing-wise. I don't care which computing machine you're using, this is a horrible algorithm. It's going to take forever to run. It's crazy. The iterative one, ugly, but nice computationally. Really nice computationally linear. We like that. Here, 2 to the n, on the order up. We can get a better approximation, but we're going to leave it 2 to the n, order up. Now, pardon me for 1 second to see if I'll carry on for today. Yeah, I'll finish this off, I guess. So, Towers of Hanoi. So, there's a story. I'm going to have to read it because I've got it in my slides, so pardon me for 1 moment while I'm reading it. There's a legend that a long, long time ago, in a place very far away, there was a temple containing 64 super sacred dishes, okay? And each dish was a little bit of a different size. So the monks needed to move, okay, each of these discs was a different size and they were stacked, okay? So you had the biggest stack, the biggest disc on the bottom, followed by the next biggest disc, followed by the next biggest disc, and so on and so on and so on, all the way to the smallest disc at the top. And there's 64 of them, okay? We've got 64 discs. And we needed to move these discs. There's these monks that were in this temple. It's very secret temple, okay? The monks needed to move these discs from one location to another. I don't know why, but it's critically important to do so. The discs are super fragile, and only one can be carried at a time. A disc may not be placed on top of a smaller disc. So it's against the rules of the universe to have a big disc on top of a small disc. You can have a big disc and have any of the smaller discs on top of it, but you are never allowed to put a bigger disc. No matter even if it's only a little bit bigger, doesn't matter. Smaller discs, never allowed below bigger discs. Bigger discs have to be underneath smaller discs. That's the rule. So the discs are present one at a time. A disc may not be placed on top of a smaller, less valuable disc. And there's only one other location in the temple besides the original and destination location. So imagine like this. We've got, the discs are here. This is sacred ground. But for whatever reason, the sacredness is running out. And we need to move these discs to over here. This is sacred ground that's recently been set up to be sacred. And we got to move the discs from there to there. But we're only allowed, for whatever reason, the gods have told us that we're allowed to put the discs here temporarily. We're only, like if I'm carrying a disc, okay, because I can only move one at a time, the discs are only ever allowed to be on that location, in this temporary allowable location, or over here in the other new sacred location. So the monks, So the monks start moving discs back and forth between the original pile at the the pile at the new location, and the intermittent location. Always keeping the piles in order, largest on the bottom, smaller ones above. It was said that when they complete their task, the universe will end. Okay? So this is a true story. I hate to tell you, this is a true story. There's a sacred temple somewhere, and these discs have to move from there to there. There's 64 of them, and there's monks moving it. Very sacred, they have to take their time. We've got to be very careful, super sacred, super valuable. And there's only allowed there to there. Now, some of you, obviously, might be very familiar with this little problem. It's called Towers of Hanoi. So, we saw how beautifully elegant the Fibonacci recursive function was, right? Well, here's another classic example, Towers of Hanoi. The puzzle was invented by a mathematician. Now, that's not true. This is a real story, but for whatever reason, to appease the masses so people don't panic that the universe is going to end, the puzzle was invented by a mathematician, Edward Lucas, in 1880. In the 1880s, pardon me. And it's based on a legend involving monks. Great, okay. It said the world would end when the monks finished their task. So the puzzle is made up of 3 vertical pegs, several discs that can be added and removed from the pegs, and the discs typo are a varying size. That typo was in there last year, I forgot to fix it. The discs start on one peg with the largest at the bottom and the smallest at the top. If this doesn't jog your memory, I don't know what else will. This is the toy. Basically, we have to move all of these to here such that they're in the same order, but the rule is you're only allowed to move one at a time. They can only ever be placed, like if you're moving one at a time, all of the discs must be on one of the pegs, and any of the discs, you are not allowed to have a smaller disc below a bigger disc. That's the rule. So, if you're to do it, we need to move all the discs from one peg to another. Only one disc can be moved at a time. A disc may never be placed on top of a smaller disc, and all discs must be on some peg except the one being moved. Long story short, here's what we would do. Here's an example. If we do that, we move there, then we move that other one. Wait, what do we do? Move that there, then we move that one there. Oh, then there, then that there, then that there, and so on, and then we get the right answer. Take your time when going through the slides to make sure you got it. It's a little process. It's actually a relatively simple algorithm. But here's the recursive algorithm. And you might hate this. You might love it. But here's the reality. We're not going to spend a lot of time investigating it. But remember how before I was emphasizing, if I asked the person at the end of the room, how many rows are there in front of you? And the answer was, well, it's just 1 plus however many rows are in front of me. Pardon me, I need to rephrase that question. How many rows are there in the room, including yourself? Well, it's the sum of the rows in front of me plus me. That's it. And if you knew how many rows are in front of you, you're good to go. So all you have to do is just, oh, well, it's the sum. Just get the answer to how many rows are in front of me plus 1, return that, done. Same idea here. If I need to move n disks from the original peg to the destination peg, here's all I have to do. Move the top n minus 1 disks from the original peg to the middle peg, the extra one. Here's what I mean. All the disks here, okay? Move the top n minus 1 here. Move the biggest 1 disk here. And then move the n minus 1 from here to there. That's it. It's easy, right? Now, of course, you're saying, well, hold on, you skipped some steps. But this is the magic of recursion. This is all the recursive call. So, we just are going to keep track of what's the middle peg, what's the original peg, what's the destination peg. By shuffling around which is which. I'm blitzing through this because we are definitely out of time, but bear with me. I move the top n minus 1 here, move the biggest one there to there, and the n minus 1 there to there. Now, you're obviously saying, well, hold on, you can't just say move the top n minus 1 from here to here, because you're only allowed to move 1 disk at a time. You're right. Now, how do I move the n minus 1 disk from here to there? Oh, well, that's easy. Move the n minus 2 disks from here to there. Then, so that's the middle one. So move the n minus 2 disks from here to that one. Then the n minus 1 disk to there. And then the n minus 2 disks from here to there. Right? That's it. Then we can move the big one. Well, hold on. How did you move those n minus 2 disks from here to there? Well, that's easy. Just move the n minus 3 disks from here to there. Then move the big one, the n minus whatever, to there. And then goes to there. We're just shuffling which is which. And if you follow through, you'll be good. And we also have to shuffle the other side. Move the n minus 1 disks from here to there. So now we're going back, right? Okay, I've moved the n minus 1 from here to there. Move the biggest one there. Now we are saying, well, how do we move these to there? Well, that's easy. Take the n minus 2, put them back there. Pretend the original one is the middle one. Move the n minus 1th one there. And then remove the remaining there. Don't spend too much time wrapping your brain around this. It's a remarkably simple algorithm, and it sounds like we're being lazy, but it'll work. It will. It's guaranteed to work. Now, when talking about the computational complexity of Fibonacci, we learned that it was 2 to the n. Basically, the trick here, for the very, very, very quick and dirty, don't do this in general, but because I don't really want to spend too much more time on this, unless you think this is critically important at this stage. This will be more important later on in like 255 and so on. But we just think, well, how many calls are going to have, like how many layers to that tree? Well, like n. And how many function calls are there per function? Well, each function is calling, like if I call this code right here, it's not really code, but it's like algorithm. If I call this, how many new function calls are there? Well, move the top n minus 1, move the n minus 1 disks again. There's 2 recursive calls. And how many layers are there? It's going to be like n. So this is another 2 to the n situation. Now, if we go back to the original story, it is said that, okay, the universe is going to come to the end. So really, the amount of work that's going to have to get done is going to be 2 to the 64, minus 1, I guess, is to be more precise. But it's on the order of 2 to the 64. Actually, not on the order, that's a precise number. So 2 to the power 64, how much work is that? Well, if we do all the math, and assuming a monk, you know, the monk moving it is getting pretty good because he's been doing it for a while. If he can move 1 disk per second, it would still take, what do we have? 558 billion years to complete. So I guess we're safe. If that monk is moving 1 disk a second, 64 disks, following this algorithm, move some there, you know, doing all that, then the amount of work that monk is going to have to do if they're doing 1 disk a second, it's still going to take 585 billion years. So I guess we're fine for the universe not ending anytime soon. So let's see. We already did this. So this is, what's the computation complexity of this? Well, it's basically starting at 0, I guess 1 to n, order n. It's iterative, it's easier. Now recursively, how many recursive calls? So let's do a quick recursive analysis here. How many recursive calls per function call? Well, if I call n, like recsum n, it's only ever going to call 1 recursive call, which would only ever call 1 more recursive call until it gets to the bottom. So at most, there's 1 call n times. It's linear. Let me take my time doing this again. I don't want to speed through that. I'm just going to call it f for simplicity. F of 6. Well, for that it's going to be 6 plus f of 5, f of 5, 5 plus f of 4, f of 4 plus, equals 4 plus f of 3, f of 3 equals 3 plus f of 2, f of 2 equals f of 2 plus, just 2 plus 1, or f of 1, and f of 1 equals 1. There we go, if you can still see it. Let me clean this up, it's kind of ugly. There. So I mean, it's still linear, right? Because we've got, should be an equals, not a plus. 1, 2, 3, 4, 5, 6. It's still linear. How many times is this function going to run in total? Well, it's going to run for the nth time, n minus 1 time, n minus 2 time, n minus 3, n minus 4, 2, 1 time. It's linear. Here, it's actually 2 to the n. This one, very bad, 2 to the n. So in real life, recursion actually pops up a lot. These ideas aren't crazy. We won't spend time doing it, but just do note that we're not doing fun recursive math for the sake of doing fun recursive math. It's actually a very natural phenomenon. So just be aware of that. Anyways, that's that for the recursive lecture. Hopefully you found it useful.